Welcome back. Starting from this section, we will start with statics concepts. We will first cover vectors and vector operations. In order to make this entire teaching process more practical and relevant, we will be using problem-based learning. I'll be giving you problems to solve, and as we go through those practical cases, you will not only learn the intuition and math behind the statics concepts, but you'll also see its relevance. You'll see how these concepts fit in the real world. And then, once you know those concepts, I will give you more problems that you can solve by yourself. I will also solve them for you in the next videos, but I highly recommend that you try solving them yourself first. Only then you will learn and solidify those concepts by trying them out on your own first. Let's get started. Welcome back. In our first problem, we have a car, this green one, let's say that it's car C, and it is being towed by other two cars along a straight road. So you have this car A here and car B, car A in red, car B in blue. So here they are again, car C, car A, and car B. And so these are the wires here. And so car A applies a force to car C at FA newtons and at 20 degrees. And this dotted line, that's the straight road. And then car B applies force, which we will call FB newtons, and it's at 70 degrees. 20 degrees is counterclockwise and 70 degrees is clockwise. The forces FA and FB are unknown. However, it is super important that the car that is being towed, car C, it is super important that it would follow the straight road. It cannot go to this side nor to that side. That cannot happen. It has to go along the straight road. Also, it's very important that the car would experience an equivalent amount of force of 950 newtons along that straight road. And that's necessary in order to overcome all those internal friction of mechanical components in this car C. And for that you have to tow this car at 950 newtons along the straight road. And so your task is to compute the correct values for FA and FB so that car C would follow the straight road with this force, 950 newtons. So in the next video, let's see how we would approach this problem. Let's learn some fundamental concepts that you need in order to calculate FA and FB. Thank you very much. Welcome back. So we need to solve this exercise where we have to calculate FA and FB so that this car C would experience force of 950 newtons along the straight road in the direction of this green arrow. But in order to do so, let's for a moment forget about this exercise and let's learn some basic concepts with which we can solve this exercise later on. First of all, in general, you have quantities in the world that you can measure with a number. For example, if I ask you, how much money do you have? You can say that you have $300 or 500 euros, and the currencies dollars and euros, they are units of money. Just like you can say that the length of this line is 500 meters and the length of this line is 2 miles. But the fact is that you only need one dimension to tell me how much money you have, or what is the length of these two lines here. So if we think about money, then I can have an axis here, and let's say it's a dollar axis, and so here you have some numbers for how many dollars you could have. Or let's say I draw another axis, which is the euro axis, and here are the numbers. And so if I have $300, then I'm here. And if I have 500 euros, then I'm here. As you can see, you don't need more dimensions than one in order to tell me how much money you have. Or I can ask you what the mass of a chair is that is in your room. And you can say that it's 10 kilograms. Again, you only need one dimension for that. One axis and 10 is here. But what if I ask you what the velocity of your car is at the moment? Can you tell me that information using one dimension only? Well, you look at your speedometer and you tell me that it's 20 meters per second. But then I ask, in which direction? Well, if the car drives on a 2D plane, then you can see that next to 20 meters per second, you also have an angle of 30 degrees here. So now you need two dimensions to fully describe the car's velocity. You have the car's speed, 20 meters per second, and the angle, 30 degrees. I can also represent them like this. I have one axis which I call V. These are the numbers, and the unit is meters per second. And then I have another axis that I call theta. That's the axis for the angle. Let's represent it in degrees right now. Again, you have the numbers here for the degrees. And so this first axis, that's the speed axis. And the second axis, that's the direction axis. And then if you put them together, that's when you get velocity. So the car's velocity is 20 meters per second at 30 degrees counterclockwise. With these two dimensions, I can fully describe the car's velocity. If I had chosen other values for my speed and direction, let's say 40 meters per second and minus 20 degrees, then this car that drives here on this 2D plane, its velocity is the following. The speed, or the v dimension, it's 40 meters per second, and then the angle theta, that's minus 20 degrees, or 20 degrees clockwise. So new speed and new direction. And now, the things that you can fully describe with one dimension only, like money or mass, they are called scalars. Note that a scalar can be positive and negative. For example, with money, you can have minus $100. That means that you're in debt. Of course, mass is also a scalar, but it cannot be negative. This is the case where mathematically something is possible, but in real life it's not. So you always need to think about the context as well. However, things for which you need more than one dimension in order to describe it, like velocity for example, they are called vectors. In order to fully describe velocity, you needed the car's speed, v, and direction, theta. You needed two dimensions, so velocity is a vector. In fact, if you think about it, then a scalar is simply a one-dimensional vector, but we call it a scalar. In addition, vectors can also be represented like this, with arrows. The length of the arrow is the car's speed, and in general it's called vector magnitude. Also this one is vector magnitude, since in the lower case the speed is twice as big as in the uppercase. Here you have 40 meters per second and here you have 20 meters per second. Then in the lower case, the length of the arrow is twice as long compared to the uppercase. Then the angle theta, it tells you about the direction or about the sense of the vector. Here it's counterclockwise, and then here it's clockwise. And by convention, it is measured from the line that is in the same direction like the positive x-axis. And so from this line, if you go like this, then your angle is positive or counterclockwise, and then if you go in this direction, then your angle is negative or clockwise. And then this one in the vector and this one in this vector, they are called vector tails. And then this point here and this point here, these are vector heads. And so if you go along this arrow, then this line that goes along this vector, it's called line of action. And here as well, if you take this smaller vector, then it points in this direction here. And so this too is line of action. Note that when dealing with vectors, then their magnitude, or in other words, the length of the arrow, it cannot be negative. It's just the length of the arrow. It goes from 0 to some kind of positive number. And then the angle theta rotates that arrow in the right direction. Finally, now you know that speed and velocity are not the same thing. Speed by itself is a scalar quantity. It does not tell you anything about the car's direction. It just tells you how fast you cover the land. However, if you pair it with the angle theta, that does tell you about the car's driving direction, then you have a velocity, and that's a vector. So speed does not equal velocity, but speed plus direction equals velocity. And now, there are many quantities that require more than one dimension to fully describe them. One of them is forces, and that's exactly what we need in order to solve our car towing problem. Forces, just like velocities, are vectors. They have both a magnitude and a direction. When cars A and B apply their respective forces, Fa and Fb, to car C, then Fa and Fb are vector magnitudes, and we need to find them. And then the direction of Fa is 20 degrees counterclockwise, and the direction of Fb is 70 degrees clockwise. So let's now try to find the correct required forces Fa and Fb. Let's do that in the next video. Thank you very much. Welcome back. Let's now continue with our car towing problem. The goal was to find the force vector magnitudes of Fa and Fb. And we know that their directions are 20 degrees counterclockwise and 70 degrees clockwise respectively. And we also know that in total, car C needs to experience 950 newtons of force along the straight road. And in order to make that happen, we need to find this vector magnitude Fa and this vector magnitude Fb. In other words, these two vectors here, they have to produce 950 newtons in this direction. What it really means is that the force vectors Fa and Fb, with their own magnitudes and directions, need to produce a combined effect, or in other words, an equivalent force vector whose magnitude is 950 newtons and direction 0 degrees, in order to make sure that the car goes along the straight road. This equivalent force vector is also called a resultant force vector, or simply Fr. It's important to understand that this vector Fr is not a real force vector. It is not physically generated by another car. It is merely a combined effect of the forces of Fa and Fb. It's a result of these two force vectors that are physically generated by two cars, car A and B. Another way to look at it is like this. Towing this car C with two cars, cars A and B, with force vectors Fa and Fb, or towing this car with car D with a force vector, which is the resultant force vector of Fa and Fb, it will make this car C behave exactly in the same way. For car C, there is no difference whatsoever. That's why we also say that FR is an equivalent force vector to FA and FB. And now, how do we get that resultant equivalent force vector from these two vectors, FA and FB? For that, we need to add vectors together, which is very easy. I will create another XY coordinate frame, and let's say that here, these axes, they are force axes. So the units here are newtons. So the horizontal line measures force in the x direction, and then the vertical line measures force in the y direction. And so what I will do now, I will take this FA vector, I'm going to put its tail where the origin is, and so I'm going to draw this vector here. Of course, it's 20 degrees counterclockwise, and then I'm going to do the same thing with vector FB, and here you have 70 degrees clockwise. The tail of the vector is in the origin, and then for the purposes of adding vectors, you can shift them around as much as needed. So I can take this FB vector and I'm gonna shift it so that its tail would be where you have your FA's head. And so I'm gonna put my FB here as well. It's the same FB that you have here. It's only shifted. And so that's how you add two vectors together. You have one vector FA, and then you take another vector, and then you shift it in such a way that the tail of the second vector touches the head of the first vector. And then, from the origin, you draw another vector that reaches the head of shifted FB. And that's your resultant FR vector. And this method is called a triangle rule. Note that you will get the exact same FR if instead of shifting this blue vector here, you take this red vector and you shift it here. So the tail of FA touches the head of FB, and then FR goes from the origin till the head of FA. And if you do both, if you take this blue vector and you shift it here, and you take this red vector and you shift it here, then even though you get the same resultant vector, but this kind of method has a different name. It's called a parallelogram rule. Both rules give you the same FR. But if you use this parallelogram rule, then you will end up having two triangles like this. And that's very good because now we can use some triangle properties in order to find FA and FB. If you look at these two triangles, then you can see that they are exactly the same triangles. That's because both of them have this side, which is FR, then this triangle has FA here and FB here, and then this triangle has FB here and FA here. So if you take the lower triangle and you turn it 180 degrees, then it will look like this. And so from all that, you know that if you have 20 degrees here and 70 degrees here, then that means that since they are the same triangles, you have 70 degrees here and you have 20 degrees here, and now we need a third angle. If I draw a random triangle, then a horizontal line, and I extend these two sides, then if I say that this is angle 1, this is angle 2, and then this is angle 3, then already visually you can see that angle number 2 here, it's also the same here. And angle number 1 here, it's also the same here. And angle number 3 here, it's the same here. So that comes from geometry. And so if you add up all these three angles here, then you will get 180 degrees, which means that the sum of all the internal triangle angles is 180 degrees. And that means that this third angle here, that's 90 degrees, because you have 180, which is the sum of all the angles inside the triangle, minus 70 degrees here, and minus 20 degrees here. That will give you 90 degrees. And then, of course, here as well, you have 90 degrees. So you have all the angles, and you have one side, which is 950 newtons. But how do we find the remaining two sides, FA and FB? Let's again draw a random triangle with different sides, A, B, and C. Let's also draw H here, which is perpendicular to A. And let's say that you have an angle alpha here, then here you have beta, and then this angle here, that's gamma. So gamma is this third angle here. And so from trigonometry, you know that sine alpha, it equals H over C. And then sine beta, it equals H over B. We can rearrange them like this. H equals C times sine alpha, and H also equals B times sine beta. But that means that this one and this one, they are equal to each other. And so if I want to, I can rearrange their relationship like this. Sine alpha over B equals sine beta over C. Then what I will do, I will draw another line here, which is perpendicular to C, and I'm going to call this line L. And so now I can write sine gamma, which is this angle here, it's L over B, because you have your right triangle here. And you can also say that sine alpha, well, that's L over A, because again, you have a right triangle here. And so that means that you can say that L equals B times sine gamma, and L equals A times sine alpha, which means that this one and this one, they are equal. And so if I rearrange them, then you can have sine gamma over A equals sine alpha over B. But this sine alpha over B, that's this one here, that also equals sine beta over C, which means that I can put an equal sign here, and I can write sine gamma over A here. And there you go, we have an important relationship here. And this relationship, it's called the sine rule. And we can use it to compute our FA and FB. Let's do that in the next video. Thank you very much. Welcome back. So now that we have this important relationship called the sine rule, let's use it to compute our FA and FB vector magnitudes. You can see that in the sine rule, if I have alpha here, then the side that is opposite to this angle alpha, which is B, it will be in the denominator here. So sine alpha over B, then you see the similar pattern here. Sine beta over C, beta is here, and then C is the opposite side to the angle beta. And the same thing with gamma. You have sine gamma over A, and A is the side opposite to the angle gamma. So if we take our triangle now, where you know all the angles, 20 degrees, 70 degrees, and 90 degrees, and then you also know one of the sides, 950 newtons, well then using the sine rule, you can write sine 20 degrees, which is here, over FB, which is the side opposite to 20 degrees, then equals sine 70 degrees, which is here, and opposite to that you have FA, so it will be here. And all that equals, you have 90 degrees here, so sine 90 degrees, and then you have 950 newtons here. So I will have 950 in the denominator. And now you can have two equations from here, and you also have two unknowns, FB and FA. You can have this equation and you can have this equation. So if I have sine 20 degrees over FB, and then that equals sine 90 degrees over 950, then you can very easily calculate FB, and it's more or less 325 newtons. Then I can take another relationship, which is this one here, and again you can calculate FA very easily, and it will be more or less 893 newtons. And there you go, car A needs to pull car C with a force FA, which is more or less 893 newtons, and then car B needs to pull on car C with a force FB, which is more or less 325 newtons. These numbers are rounded, so a calculator would give you a slightly more precise number for FA and FB. And so if these are your vector magnitudes, and FA is at 20 degrees counterclockwise, and FB is at 70 degrees clockwise, then their combined effect, or their resultant force, will be 950 newtons, 0 degrees. And so here I've made this animation in Python as well, so you can see that this is FA, 893 newtons, and then FB, 325 newtons, and if you use this parallelogram rule, then in the end you will end up with a resultant force, which is this one here, 950 newtons. And this theta here, which is 70 degrees, it's this angle here, where this vertical line is. And now what I will do, I will vary this angle theta. So 20 degrees here, it will stay the same, but I will vary this angle here, which is right now 70 degrees clockwise. Here you can see that I have made this theta 45 degrees clockwise. You still have 20 degrees counterclockwise here, but now here's 45 degrees clockwise, and now you can see that while I keep the resultant force the same, 950 newtons, my FA and FB are now different. However, the calculation method is exactly the same like I showed you before. And now let's make theta equals 20 degrees. You can see that when theta equals 20 degrees, then both FA and FB have the same magnitudes, 505 newtons. And then according to the parallelogram rule, you still get your FR equals 950 newtons. But it makes sense that FA and FB are the same. That's because in both cases now you have 20 degrees. You have 20 degrees counterclockwise and 20 degrees clockwise. Now you have this situation. You still need to have 950 newtons here, and so you have 20 degrees here and also 20 degrees here. That's the theta that I have been varying. And so already from the symmetry, you can see that there is no reason why FA and FB would not be equal. So when you see symmetries like this, then without any calculations, you can already derive some information. You don't know exactly what FA and FB are, but you know that FA equals FB, and that can speed up or make your calculations easier. So keep an eye on the symmetries. And now, what if instead of theta equals 20 degrees, I will make theta equals 10 degrees? Well, then this is what you will get. FA is 330 newtons, and then FB is 650 newtons, a lot bigger than FA. So what is the pattern that you see here? When theta equals 70 degrees, then FA is considerably greater than FB. You can see that this blue vector magnitude is quite small compared to the red one, while the resultant force is still 950 newtons. Then, when I make theta equals 20 degrees, then both force vector magnitudes are the same, and the resultant force is still 950 newtons. And finally, if I make theta equals 10 degrees, then now FB is considerably larger compared to FA, and the resultant force is still 950 newtons. So the pattern here is clear. The car that has a smaller angle compared to another car experiences a greater force in the cable. So in this case, the blue car has a smaller angle, just 10 degrees, and therefore this cable here, it experiences more tension force compared to the red one. Finally, I want to point out two more things. First of all, the sine rule that you have in this form, we can also represent it like this. B over sine alpha equals C over sine beta equals A over sine gamma. So I can simply reverse the numerators and denominators here. It's like 1/2 equals 2 over 4, 4 over 8, or I can also have 2 over 1 equals 4 over 2 equals 8 over 4. The same thing, there is no difference. And then secondly, now you know how to add two vectors. When you have vector A and then vector B, then if you want to add them, then you will take your vector A and then you shift vector B in such a way that the tail of B touches the head of A, and then the resultant vector, it starts from the tail of A up until the head of B. So this is your resultant vector. But how do you subtract vectors? How much would be A minus B? Well, in reality, it's also addition. You can write it like this: A plus, and then here you have minus B. And now if this is B, then minus B would be the same vector, only in the opposite direction. And now you will simply add A and then this blue vector. So your A vector is still here, then this is minus B, and then this would be your resultant vector. You'll simply have another triangle. Thank you very much.